Alright, the next thing we're going to look at is the cryosphere. That's the part that's frozen. And the first thing we want to be familiar with are the components of the cryosphere. And these are listed in a couple of places in the text, table 2.1 and figure 2.12. So let's attempt to look at both of those. Here we go, table 2.1. Alright, so what we're showing here are two things: the surface area covered by each of these components and the mass of ice. Let's see, what is it? Mass equivalent to meters of liquid water. I'm going to do some shading here. So the mass numerically equivalent to meters of liquid water. Alright, so let's have a look, see what we've got. We've got the Antarctic ice sheet. That's over the South Polar Cap. Covers 2.7 something, 2.7 square meters probably, or 2.7. Oh, area is expressed as a percentage, I probably should have read this first, of the area of the surface of the Earth. So 2.7% of the Earth's area is covered by the Antarctic ice sheet, and it's very massive, 53 units of mass. By comparison, Greenland, which is also ice over solid rock, much smaller, 0.35%, and 10 times smaller in terms of mass. Alpine glaciers, teeny weeny, 0.1% of the world is covered by alpine glaciers, and as we'll see in a minute, that amount is shrinking, and only 0.2 units of mass. Arctic sea ice in March, when it is most expansive, 3%, 0.04 units of mass. As we'll see in a minute, sea ice isn't that thick. It may be just a couple of meters thick, versus the Greenland ice sheet might be a mile thick. Antarctic sea ice in September, when it's at its most extensive, 4%, 0.04 units of mass. Seasonal snow cover, you might want to think of places like Canada or northern Wisconsin. 9% of the surface of the globe, probably most in the northern hemisphere, but a very small amount of mass. And lastly, permafrost. Permafrost is something that we didn't talk about before. 5% of the globe is covered with permafrost, and 1 unit of mass. So let's go have a look at these again. Here we go. This is figure 2.12 in the book. Well, we've talked about the polar ice cap already. That's the North Polar ice cap. We'll look at some video of it shrinking in a little while. And then here's Greenland in red. Glaciers and ice sheets covering Greenland. Blue is seasonal ice, so you can see that up in this region here, and here in the Bering Straits and down into Hudson's Bay. Seasonal ice means that it's ice covered in winter and open water in summer. According to this, the white stuff, perennial ice, but as we'll see, that is changing dramatically right now. Snow extent, the northeast down through Colorado, but north of this line we have permafrost, and permafrost is that part of the land where to some extent the land beneath the surface is frozen, and so that there is some water locked up in that as well, and we'll be looking at the permafrost in a few minutes. Whoops, so let's go back here. I've just shown you table 2.1. You need to have some knowledge of how much of ice there is in each of those categories. It's the sort of thing that can pop up on a quiz. Now, let's think about what the cryosphere does, because we've described what the cryosphere is. It's frozen stuff. And why do we care about it? Well, first of all, it provides something that we call thermal inertia. Okay, so all students know what inertia is. it's the inability to get out of bed in the morning. That's inertia, a slowness. Thermal inertia is also a slowness in warming up and cooling down. So the cryosphere provides a thermal inertia. When the sun shines, the frozen part, the cryosphere, doesn't warm up very rapidly, and it slows down the warming of everything else. Secondly, as we all know, the cryosphere contributes to the albedo of the planet. That's the brightness, or how much of the planet is reflecting incoming sunlight. And that's a concept we'll be talking about more in chapter something later on, chapter 4, I think. As we've already seen, the cryosphere influences the thermohaline circulation. Okay, as sea ice is forming, as sea ice is forming, cold, salty, dense water is sinking near the polar and the south polar ice caps and driving the thermohaline circulation. So when you look at it from this perspective, there are three relatively important things that the cryosphere do for us that influences the climate and also day-to-day weather. So we do care about those things. And then the last thing is that sea levels are impacted by the cryosphere. As more water freezes out into the polar ice caps, global sea levels go down a little bit, and vice versa. If the ice caps are melting, global sea levels should be going up. Now, let's think about what's happening over land, and we can think about figure 213. Figure 213 is one of the figures in the book that I don't have access to. But you can look at it for yourself. It's on page 33. We have Greenland, and Greenland is covered by a vast thickness of ice. And here's something to think about. Let's draw a little sketch here. Suppose that at the bottom here, this is Greenland, the rocky part. And let's suppose we're far enough back in time where there's no snow. And then one day it snows. And so you get an accumulation of snow down here at the bottom. And then after a while, the snow turns to ice. All right. And then the next year, I'm going to have to take all of this off to make my point. The next year, come on, there you go. Next year, now we've got some ice down here, and it snows again. And so you get some more snow accumulating on top of the old ice. Okay? And then same thing happens the next year. Only by now you've got a couple of years worth of ice built up. Okay? That's how this works. So that after long enough over Greenland, you have a vast, thick layer of ice. And roughly speaking, it can be up to 1 mile deep. Okay, that's a rough number, but it's not 1 foot deep, and it's not 1,000 miles deep. It's about a mile deep. And the important thing to realize is that the stuff at the bottom is old ice, whereas the stuff at the top is new ice. Now, it turns out that as these snowflakes accumulate and form the ice layer, there are little tiny bubbles of air trapped in between. And it's possible to drill down to the bottom of the ice and carefully extract these little tiny air bubbles. And when you do that, you get to know the composition of the air at the time that this ice was formed. And between Greenland and the South Pole, Antarctica, we can go back hundreds of thousands of years to know something about the composition of old ice and old air at the same time. So that's what allows us to fill in this table here. The Greenland ice cap, the ice is up to about 100,000 years old at the bottom. Over Antarctic, about 500,000 years old. And by doing ice cores, we can get information on past climate. And we're going to talk a little bit about past climate in the next section, and we'll talk about ice cores there at the same time. The other thing to talk about are alpine glaciers. Alpine glaciers just means in mountains. Things like Glacier National Park in the United States, things like glaciers in the Alps in Europe, stuff like that. They're much smaller, they move very fast, and remember that although it looks solid ice, it's actually a kind of a liquid, so ice flows downhill. And that's what glaciers are, just rivers of ice flowing slowly downhill. And they are shrinking rapidly. And to prove that, I found a website. You can probably find a website to prove anything you want to prove. And this is something called Live Science. And it has a series of photographs of glaciers before and after. All right, and I think that these might be in Glacier National Park. So here is something called the Agassiz Glacier, taken in 1913. See this glacier up in this region here. And in 2005, it's basically gone. This is the Blackfoot-Jackson Glacier Complex in 1914. See all this ice here? In 2001, it's much retreated. Some of these pictures are better than others. The Boulder Glacier in 1932, and the same view today. The Cheney Glacier Terminus in 1911, and in 2005 it's virtually not there. Let's just look at one more. The Grant Glacier, this whole thing here. Well, actually, that doesn't look as though it's changed very much, so let's find one that has changed. This is the Grinnell Glacier. I think it's this stuff down here. And now, nothing. Of course, it's in color. That helps. There's a pond here. I can't tell if this is ice or a pile of rock. This is probably ice. But a dramatic change. So there's plenty of evidence from all over the world that the extent of alpine glaciers is rapidly changing. Let's talk a little bit about sea ice, and again we're talking mainly about ice up at the North Pole and around Antarctica. Sea ice is not very thick. Actually, when it forms, it's not very thick at all, but it can thicken up during the winter. So typically only 1 to 3 meters thick. And it's very good at insulating the ocean. So once ice begins to form, then additional formation is slowed down tremendously. Let me see if I can convince you of why that is with yet another amazing diagram. Let's see. So here's the air, and down here is the ocean. And let's just assume we're up near the North Pole. So it's very cold water. Now, just for fun, let's see what we can do in terms of a different color. So, in the middle of winter, we know that the ocean is cold, but, it's only about 32 degrees Fahrenheit. I wouldn't want to swim in it, but it's not that cold. The air is also very cold, and in that case it might be minus 40 degrees Fahrenheit. So what happens when there's such a huge temperature gradient? I'll tell you what happens. enormous amounts of heat get transferred from the less cold place to the more cold place. So you got heat transfer going on from the ocean to the air. When you have a very cold air mass of air coming out of the North Polar region heading south into America, this causes a transformation of that air mass. It heats the air mass up and also puts some vapor into the air as well. So that's why down here we never see anything remotely this cold, because the air mass has been modified on the way down. Now let's think about what happens when you add some sea ice, even a relatively thin layer of sea ice. Then the transfer mechanism is shut down tremendously. Let me think how I am going to show you that. I don't know, so I'll just cross out every other one of these. So the ice acts as an insulator, for what that's worth. So let's go back to here. The ice is not a solid layer, so there's some photographs here in the book. This is one photograph showing that you have chunks of ice and open water in between. Actually, this thing looks like an iceberg to me. This is probably a better picture taken from above of what sea ice looks like, and it's clear that it's not one continuous slab. So you have a slab of ice here, open water. Slab of ice here, lots of little chunks of ice here, and open water. So that in fact when you try to do the physics of this more carefully, you have ice is only partially present in chunks like this, and in between you still got quite a lot of heat being transferred from the cold water up to the air above, and that actually makes it become an extremely difficult problem to look at. The North Polar ice cap is moving. There's no land under here, so you have this giant slab of ice and it's free to do whatever it wants to do, and scientists have studied the motion, and basically it's a big kind of swirl like this, quite slowly. That's clockwise as you look down on the North Pole, with ice flowing out east of Greenland into the North Atlantic, and down here west of Greenland eventually into the North Atlantic. And if this diagram went down far enough, you would see that this is how you get icebergs that sink ships like the Titanic, which are sailing across the Atlantic. One last thing about sea ice, and that is to talk about the loss of sea ice in the Arctic. And here is a link to a really nice discussion and video. This is what it looks like. When you start this thing up, you'll get a little video. It's 6 minutes long, and at the beginning you'll see some nice animation, time-lapse animation of sea ice motion in this region, and you'll get to see the rotation, you'll get to see the ice flowing out past Greenland, and you'll also get to see the loss of sea ice. Last topic is permafrost. Permafrost refers to that part of the land that is more or less permanently frozen. There is plenty of evidence, and in addition there's plenty of computer simulations to show that we expect the biggest effects of global climate change at highest latitudes, and this is having a big impact on the permafrost, and I've got a little video clip to show you in a minute about that. But a lot of people are paying a lot of attention to the region of the planet that's called permafrost. Let's just have a quick look at this figure, 2.17. Make sure you understand what's being shown in this figure. Let's see, where are we on color? Yeah, that looks good. All right. Down this axis is depth in meters from the surface. 0 meters depth, so here you are standing on the surface. Okay, that's depth down there. And along this axis is temperature in degrees Celsius, and here's the freezing point. So this is above freezing over here, and down here below freezing. Let's change the color. Let's go with green. These blue lines each represent the temperature profile. Temperature profile that you would measure from the surface on the way down with instrumentation if you were to bury some instruments underground. In summer, it's above freezing at the top and at some depth, and here it looks like I'd say about 3 meters. In this example, 3 meters down, the ground becomes frozen. Mean time in the winter, in this case, in this example, it's cold at the top. -4, stays frozen all the way down to, I don't know, somewhere down here, 50 meters below the surface. Okay? So, you get deep enough and the ground might be relatively warm, but that's a long way down, 50 meters down. In the top 3 meters of the soil, it actually may be above freezing in the summer, and it freezes in the winter. And then below that, this whole region is always frozen, and hence the term permafrost, permanently frozen. So that's what permafrost is, and we saw a figure earlier showing the extent of permafrost in North America anyway. Something that we're worried about in terms of the permafrost is the leakage of methane. Down here, where the ground is frozen, you've got buried carbon in various forms. Old vegetation that died and just is sitting there, old animals that died and is sitting there and is locked up in the permafrost. But as the permafrost is leaking, then we're having a situation of methane, CH4, beginning to leak out of the old permafrost layer into the atmosphere. Methane we care about. Methane is a greenhouse gas. So if you can see this link here, there's an NBC news clip that I want you to visit and watch. I'm not responsible for the commercials at the beginning of the thing, and I'm going to stop it and let you watch it for yourself. But it'll tell you and show you some cool images of what happens when this methane leaks out.